Okay, welcome to lecture 3 of the planets. Believe it or not, with the end of this lecture, 10% of the course will be over. Don't cheer yet, the final exam is coming fast. Bad news. Today we're going to have one of the most important lectures of the semester. We're going to talk about what you see in the night sky, stars, planets, the moon, other phenomena, the motion of all of those objects during the day and during the year, and most importantly, we're going to discuss why you see the motion that you do of the moon rising, the sun rising and setting, the stars rising and setting, the constellations. We'll try to give you a sense as to why the night sky is the dynamic place that it is, so that when you look up into the night sky, maybe after class today, if there isn't much fog, you'll be able to understand what it is you're seeing when you see the moon or the sun or the stars moving or setting. So those are the topics. Let me first mention one thing, which is homework. There is the first homework assignment due tomorrow at 6 p.m. And of course, almost all of you have already started it, I know. To remind you, it's all on Mastering Astronomy. If you somehow or other have not registered for Mastering Astronomy, you need to do so. I'll remind you, if somehow you don't have your access code, you get a 1-week reprieve. I'm pretty sure you can get into Mastering Astronomy temporarily for a few more days without actually having an access code, and that may allow you to register and do the homework. But after that, then you do have to have the access code. So the homework assignment is due for chapters 1 and 2 tomorrow, as you see over here, September 5th at 6 p.m. And they're actually kind of fun problems. They're problems where you have to figure things out. There's a homework assignment due a week from tomorrow, which you can anticipate already. It's chapter 3, again in Mastering Astronomy. It, by the way, is already there. So there it is, September 12th due. So you can actually look ahead to the homework assignments in your future. Okay, now I'm going to introduce you to the night sky and give you a tour, and hopefully a tour with signposts so that you'll be able to find your way around the night sky for the rest of your life. Here's what the sky looks like. I don't know, can the lights be dimmed a little bit? You guys who are running the lights, it might be helpful to see this with the room a little bit dimmer than it is. The sun almost set. I think that's better. What you're seeing here is what the sky looks like tonight. When you walk out of class, of course, it'll still be daytime, but an hour later the sun will set, the stars will be visible. They are, of course, out right now in daytime. It's just that you can't see the stars against the glare of the daytime sky, but the stars are out 24/7. And here's what the stars look like. You may be able to recognize some of the constellations, the arbitrary clustering of stars. Let me show you some signposts. There's a brilliant star that's nearly overhead at the beginning of the night, and it's called Vega. It's right there, that star. You can pick it out because it is almost exactly overhead at 8 or 9 p.m., and so it's quite distinctive, and it's a white color, almost a bluish white color, so this star stands out against other bright stars because of its brightness and its white color. We'll be talking about why stars have colors later in the semester. In addition, there's another bright star in the west, about halfway down angularly, 45 degrees from overhead, or in other words, 45 degrees up from the horizon, is this star called Arcturus. It's almost as bright as Vega, but it has a distinctive yellow, almost orange color to it. So you might be able to look up into the night sky and just ask yourself, where are the two brightest stars? Ah, there's Vega overhead, and if you can figure out which way is west, by the way, that's toward the Pacific Ocean, of course, toward the bay, toward San Francisco, toward the ocean, that's where you'll see Arcturus about halfway down toward the western horizon, where the Golden Gate Bridge is. Okay, so those are two signposts. Now let me introduce you to a couple of constellations. One of them is among my favorites. It is called Cygnus, which is the word for swan, because this configuration of stars obviously looks exactly like a swan. If you've drunk the right stuff beforehand. And if you look pretty carefully, there's some faint lines. It's actually a big northern cross in the sky. There's a star here, 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 here. That's the long axis. And then there's a star here and here. So there's a long axis and then a short one. So it's sometimes called the Northern Cross. Cygnus is a very prominent constellation because it goes right overhead and it's not too far from Vega. So that's one constellation. The other one you already know, but let me point it out to you. It is called the Big Dipper. And it's coming up in the northeast nowadays. Sorry, the northwest. You see there's west. The northwest. Here's the Big Dipper. There's a star there, there, there. That's the handle of the dipper. And then the bucket is here. There's 4 stars. So there's 7 stars in the Big Dipper. And if you look north and a little bit west of north, you should be able to see it. There's a trick if you want to connect the dots. If you take the handle of the Big Dipper right there, there, and there, you see those 3 stars that you can kind of hold. That's the handle of the bucket part. If you take those 3 stars as if they were an arc, the arc points to Arcturus. So the handle of the Big Dipper arcs to Arcturus. So kind of a way to use stepping stones to find your way around the cosmos. So those are the 4 things in the night sky that you might want to try to keep track of and look when you get a clear night coming up. These 4 things, Vega, Arcturus, Cygnus, the Big Dipper. Try to find them yourself in the real night sky, not the fake night sky. Let me give you a little practice. There's the night sky. Can you find Vega? It's not that easy. And what about Arcturus? There's Vega. There's Arcturus. And then what about the swan? You can kind of see Cygnus, the swan, because fortunately, in this version of the night sky, there are lines connecting the stars. Every time I look in the night sky, I never see those lines. Don't know why. I never get to see the white arrow pointing to any of the stars either. Too bad. But there's Cygnus to remind you, and then the Big Dipper up in the northwest. And if you're diligent, maybe on a Friday night, looking up into the night sky with your sweetie, you might notice that over the course of hours, the stars slowly move. They go from east to west. So all of the stars you see here will slowly but surely set in the west because the Earth is rotating in the other direction, carrying you in the opposite direction, so the stars appear to be going the other way. We'll talk about that more in 2 or 3 minutes. So this is your sort of home quiz to look up into the night sky. Now, you've made many astronomical observations in your lifetime. You may not be aware of how much astronomy research you've done. Let me tell you some of the observations you have already made. You've already noticed that the sun rises in the east every single morning, not in the west, not in the north, not in the south, always in the east, or roughly so. And the sun goes overhead, or approximately so, and the sun always sets in the west, approximately. Always happens day after day. You can count on it. The moon and the stars, if you've been observant, they too rise in the east. If you watch for a couple of hours, you'll see the moon get higher and higher. The stars get higher and higher after they rise in the east. And then both the moon and all the stars eventually go somewhere near overhead. And then over the course of 6, 8, 10 hours, they begin setting in the west. About 12 hours between the rise and the setting. So that happens every single 24-hour period. Every day, all of the objects in the night sky rise in the east, and 12 hours later, they set in the west. We have to explain that. You've also made observations during the year. You know that in the summer, the sun rises higher in the sky, going nearly overhead, depending on your latitude, and the sun stays up longer during the summer months. No matter whether you lived your childhood in Perth or Croatia, south or north, it's still true that in the summer, the sun goes up higher, and it lasts longer during the daytime. So that's interesting that no matter whether you're in the south or the north, summer always means the sun goes higher overhead and stays up longer. Of course, that makes the days hotter. The seasons are very regular. You all know that. 4 seasons every year. We have to explain why they're so regular. Another observation all of you have made is the phases of the moon. All of you have seen a crescent moon, a half of a moon, which we call a quarter moon, a moon that's a little bigger than half, what we call gibbous. You've all seen a full moon. We have to explain the phases of the moon. There are also tides. Now, why am I talking about tides, ocean tides? Well, the tides come and go during a day. There's high tides and low tides during a day. There are also certain times of the month when the tides are especially high and also especially low. Why is it that during a month you get high highs and low lows? So these are some of the astronomical phenomena. There are others that you all have noticed, and we'd like to construct a theory, some kind of a toy model, a tinker toy model that has the moon, the planets, the earth spinning, the sun. Everything that we've observed must be explainable. It's not just a happenstance, just luck that the moon goes through phases or that we have summer, winter, fall, etc. These phenomena that are related to the objects in the universe must have some causal connection between how they behave and what we see. Must be. And we have to be a little bit concerned that sometimes what we see lends itself to an easy interpretation that actually is wrong. Sometimes when you try to understand what you see, you construct a theory, a model, an idea, but it turns out that with more observations or more experiments, you realize your idea just isn't right. And this is the hallmark of science. We're going to talk more about that later. So let's see if we can understand all of the phenomena that I've already mentioned so far, that some kind of a theory that connects everything. Well, let's first start with the night sky. I mentioned the word constellation. I felt embarrassed that I did that because a constellation is really make-believe. It's something we humans have constructed. Stars in the sky appear to be clumped together And those clumpings of stars are entirely a figment of our imagination. Many of the stars are much farther away than the other stars, and so the clumping of stars is fictitious. The constellations are a fake. You can see that here in this diagram. The Earth is at the center of this diagram. There it is. And the stars appear to be, in some sense, glued to a great glass celestial sphere that surrounds us. We look up into the night sky, we see the pinpoints of light as if they're light bulbs very far away, but of course they are luminous, but they're at different distances. And so you see that whereas the stars may appear to be clumped here, the stars are actually at very different distances from each other. So any constellation like the Big Dipper or Cygnus or the Orion constellation, those apparent clumpings of stars are really just apparent. The stars may be nowhere near each other. They could be hundreds of light years away from each other. So constellations are sort of a way to have landmarks in the night sky for our human enjoyment, maybe our human stepping stones to find our way in the night sky. But constellations aren't really physical associations. They're not a real part of the universe. Nonetheless, the constellations have been named, and the Arabs did the best job, the first job of naming the constellations. Most of them today, the constellations still have the names that the Arabs, ancient Arabs thousands of years ago gave to them. The Greeks and Romans added a few more constellation names. So we still have them today, but they're not anything to really think about. Now, I mentioned this kind of make-believe model of the night sky as if there were a giant crystalline sphere around us. And here it is again, the Earth in the center. And then you can imagine, again, as a kind of a cosmic map, thinking about the night sky as if all the stars were plastered on it. It's just a way to sort of walk around angularly. And in particular, let me point out some of the signposts in the night sky on this imaginary celestial sphere. By the way, those of you who remember some of your math from high school, you remember spherical coordinates. There are other types of coordinates, Euclidean coordinates and so on. This is a spherical coordinate system in which we're basically locating all of the stars in angles like latitude and longitude on this sphere. So you can say, hey, that star is at latitude blah and longitude, something else. So it's a way to locate in a coordinate system the stars, the galaxies, the moons, the planets. So let's talk about the coordinate system. The sky looks like it's a two-dimensional sphere, so let's go with it. We call it the celestial sphere, and it's a two-dimensional coordinate system for the sky. We can't tell with our naked eye how far a planet is or how far a star is, but we can see angularly where they are on this sphere. The Earth, we imagine, is at the center of the universe, which of course it isn't. And then we can start putting coordinate markers like an origin. And one of them is the North Celestial Pole right there. Where is the North Celestial Pole? Well, you take the Earth's spin axis, and there's the North Pole of the Earth, and you extend it to infinity. And that northern polar axis of the Earth pierces the imaginary celestial sphere, and we call that the North Celestial Pole. Obviously, there's a South Celestial Pole as well. There's the North Celestial Pole. There's also a celestial equator. It's this thing here. What is the celestial equator? Well, it's the Earth's equator projected out to infinity, extended out as if you could take the Earth's equator and just make that hula hoop larger and larger and larger until it extends out to the stars. And that gives you an imaginary circle in the night sky, which is the extension of the Earth's equator. That's called the celestial equator. Now you have a pretty nice coordinate system. An equator, you have a pole, you can start measuring angles to specify the positions of planets and stars and galaxies. So let's go a little bit farther. We have our north celestial pole there. I've marked some of the constellations. The celestial pole and the celestial equator are still there, as you see from before. Now there's another thing that happens during the year. Listen carefully. This is a little tricky, and it's going to get a little bit more complicated in the next couple, 3 slides. If you mark where the sun resides in this celestial sphere, every single day the sun is sitting in front of somewhere on that celestial sphere. The next day, the sun sits in a slightly different position. And the next day at noon, say, the sun is in a slightly different position. It moves relative to the background stars. And that locus of points, the set of points where the sun resides day after day after day during a 365-day year, that's called the ecliptic. It's the sun's path against the star's background, the celestial background. And here I've marked with these yellow dots the position of the sun one day after the next. I didn't actually show every single day. The sun appears to move against the background stars. Now you can foreshadow where I'm heading. The sun is way too massive and way too large to be the thing that's actually moving. The reason the sun appears to move against the background stars is that we, on the Earth, are orbiting the sun. We're taking a trip around the sun, and I want to now show you how that works. This is, again, takes a little bit of thought. There's the sun. Let's imagine it to be stationary because it's so massive, it's not going anywhere. But here's the Earth on January 21st. The Earth would be here on February 21st, March 21st, April 21st. So let's mark the Earth on, say, January 21st. And you might then ask, where does the sun appear to reside relative to the stars, if you could see them, which you can't because it's daytime, but if you could, where would the sun reside relative to the stars? Well, take a little arrow and point from the Earth to the sun and look at the stars in the background. And you can see very easily, well, if it wasn't for the fact that it's broad daylight when the sun is up, the sun indeed is sitting in front of some constellation of stars. Yeah, it's a fake constellation, but these stars are there as markers in our coordinate system. And on January 21st, the sun, if you could turn it off like a light bulb, would sit in front of the constellation Capricorn. Just so happens. Now, what about a month later? A month later, the Earth moves in its orbit, as shown by this blue arrow there. And so a month later, it's February 21st. And now when you look at the sun, don't actually do this, you'll see that the sun resides in front of a different constellation. Why? Because the Earth has moved a little bit. And now the sun appears in front of Aquarius. What this all means is that the Earth, as it orbits the sun, causes the sun to appear to move eastward relative to the background stars, relative to the celestial sphere. The sun appears to march its way against the background stars, going all the way around, taking one full year for the sun to do this dance. You can see the problem. The sun isn't actually moving, but it appears to be moving. Any smart person 1,000 years ago or 10,000 years ago would have noticed that the sun is moving relative to the stars and thought that the sun was going around us, taking a full year. We, of course, know better, and we'll talk in this semester how we know that the Earth is actually the thing that's moving. You see, here's where the Earth will be on March 21st. It'll be in front of Pisces. And so now I'd like to give you a quiz if you have your 4 colored pieces of paper. And here is the quiz. If you don't have a 4-colored piece of paper, we have very generous graduate student instructors who will sell you a colored piece of paper for $25. Very wealthy students here. Very nice. So here's the question. Are you ready? Today is September 4th. It's almost September 5th. And in fact, it is September 5th in England. Isn't it? Yes, it is. On September 4th, my question to you is, what constellation will the sun be in front of? In fact, what constellation is the sun in front of today, September 4th? And there's 4 possible answers: Taurus, Pisces, Cancer, and between Virgo and Leo. September 4th. Well, you want to show me your answers? Well, I'll tell you what I see. A lot of letter D, as in dog. And that's between Leo and Virgo. Let's see how you figured it out. Yeah, that's right. And that's because on September 4th, we're between the August 21st and the September 21st. And so halfway, roughly in between, point to the sun. And yeah, the arrow, what's behind the sun are the constellations, sure enough, Virgo and Leo. How about that? So the sun appears to move along the celestial sphere day after day after day during a year, following this path that we call the ecliptic plane. But remember, there is no real motion of the sun. It's actually the motion of the Earth. So the ecliptic plane is not the plane in which the sun moves. The ecliptic plane is the plane in which the Earth, we, move. Okay. Now, in addition, while everybody in this room feels quite stationary, if you're sitting down, you look around you, it seems perfectly obvious that you're stationary, but it couldn't be farther from the truth. You're spinning on a globe called the Earth, of course, and a typical speed at a latitude like, say, here near Mexico is about 1,550 kilometers per hour. We are rotating every minute of our lives. We're spinning, we're moving at a very high speed toward the east, as you see from the arrows. We're moving toward the east. The whole Earth is spinning at a speed of about 1,500 kilometers per hour, which, by the way, is something like 1,000 miles per hour. 1,000 miles per hour is past the speed limit. In case you didn't know what the typical speed limits are, we are cooking. We are really boogieing toward the east. The distance from San Francisco to New York City, 3,000 miles. And we're traveling 1,000 miles an hour. So we will literally be very close to the East Coast in just 3 hours. Of course, by then, the East Coast will have itself moved. But we're moving that fast. We're essentially zipping toward the East Coast every minute of your lives at 1,000 miles an hour. So that's what's happening all the time. And of course, it has consequences for what you see in the night sky. Because if we're here on the Earth, boogieing to the east, like you see in this black arrow, as we curl around the corner, the night sky is left behind. So all the planets and the stars and even the moon, they're just sitting there. Maybe they're moving a little bit, but we're just boogieing around it 24 hours a day going around the clock here. And so the fact that we're going to the east makes it appear that the sky and all of its constituents are moving to the west, because we're falling off the east side, leaving everything behind us. So the red arrows are supposed to indicate the apparent motion of the night sky, which is entirely due to our motion. So here's a summary of all of that. There's an apparent daily, every 24 hours, motion of the night sky. All the objects in the night sky appear to, well, rise in the east and set in the west. You all knew that, but the reason, of course, and you also knew this, is that it's us that's moving, not the night sky. We are rotating to the east, taking 24 hours to go around, and as we go around the corner, so to speak, the sky appears to itself go around the corner in the other direction. And so objects are always setting in the west, and they rise in the east. Is that true if you're in the southern hemisphere? What if you live in South Africa? Do things still rise in the east and set in the west? Or is it opposite? You might want to think about that a little bit. So, to summarize, the Earth spins on its axis. We're carried to the east. The sky just appears to rotate in the opposite direction. If you look due north, suppose you look toward the north celestial pole. I have to admit there's a star very close to the north celestial pole called the North Star. You've all heard about it. It's sometimes called Polaris. So there's a star very close to the north celestial pole. You can imagine staring not only at it, but also the surrounding stars, like the Big Dipper. And if you watch those stars, you'll see that they appear to pinwheel around, spin around the north celestial pole, taking 24 hours. They rise kind of in the east, and they set kind of in the west. They don't actually rise and set because the stars near the north celestial pole just go around and around and around the north celestial pole. Okay? By the way, if you happen to be standing on the North Pole, if you travel to Alaska, keep going north, when you're standing on the North Pole, the spin axis of the Earth goes right through your body and it goes straight up to heaven. And that's where the North Celestial Pole is. So, of course, you're spinning around every 24 hours. There's one day. There's another day. What do you see? The stars just appear to be going around you counterclockwise. But it's actually you that's spinning around as if you're on a turntable on a record player. And the same, of course, you could say if you're at the equator. Suppose you walk all the way to the equator. Well, when you're at the equator, the stars appear to rise in the east. The sun rises in the east. The moon rises in the east, perpendicular to the horizon. And because you're on the equator, they go right overhead, nearly so, and then set in the west. That's very different from what you see at the North Pole, or if you were standing at the South Pole, for that matter. Okay, and I'm not going to give you a quiz, but I could ask you just as a very quick question. The moon sets in the west. It will set tonight in the west. If you happen to be up, it'll set, I think it's going to set around 1:30 a.m. And so the moon actually will set in the west. And you might ask, well, why does it set in the west? And I think you know the answer. It's not the moon that's setting in the west. It's us during the last few hours before it sets that got carried in the other direction. Okay, so let me sort of bring all of this to a summary. The celestial pole can be shown on a carefully drawn now map of the celestial sphere. And let me draw it a little more carefully than I've drawn it so far. You'll see pictures like this in your homework. There's the Earth. There's the spin axis of the Earth. And the North Celestial Pole, of course, is an extension of that spin axis. There it is. There's the North Celestial Pole. The Earth is spinning to the east, so we're going that away. And there's a little person drawn on the Earth there, standing on southern Europe. And that person is getting carried to the east toward Russia. And you can define a point that's directly over your head, no matter where you are during your entire life. You can always define a point that's the position directly over your head. It's called the zenith. It's just a name. And so you see here the word zenith. Notice that directly overhead where the zenith is not the same as where the North Celestial Pole is. Why? Well, because you stand at a certain latitude. If you stood right at the North Pole, latitude 90 degrees, then sure, the North Celestial Pole's right overhead. But as you take a walk from the North Celestial Pole and you walk your way down to this latitude, now there's an angle. You see that angle? Right there, that angle? That's the same angle as the angle you walked along the surface of the Earth. Whatever angle in latitude you walked, that's the angle between the North Celestial Pole and overhead, the zenith. There's also a gray plane. You see this plane here? That's called the horizon. It's kind of a funny way to draw it, but I'm used to it now, so maybe you can get used to it. Wherever you're standing on the Earth looks flat. That's, of course, because the sphere of the Earth is so huge that this sphere we live on appears to be flat locally. Within a kilometer or two, it looks flat. But we live on a sphere. Nonetheless, you can define the horizon to be the plane that's tangent to the sphere, the floor right here, for example. And so that defines the horizon plane. There's a horizon. It extends out as far as you can see in all directions, and that's what this horizon is here. So this person has a horizon. That person can see all the stars and the planets above the horizon here, but they can't see anything below the horizon because the Earth is in the way. So that's pretty cool. You can see, for example, that, and this is a very interesting point, that the North Celestial Pole has, as I mentioned, an angle above the horizon and an angle from the North Celestial Pole. It turns out the angle between the North Celestial Pole and the horizon, that elevation angle, is equal to your latitude. You could kind of think about this for a half a minute, and you could convince yourself that the angle between the North Celestial Pole, that's here, and that the North Celestial Pole has an angle above the horizon. That's this angle. There's the horizon. There's the North Celestial Pole. There's the horizon. There's the North Celestial Pole. There's an angle. And you can convince yourself by doing 10th grade geometry that that angle is equal to your latitude. By the way, the latitude in San Francisco, 37 degrees. Los Angeles is about 34 degrees. New York City, I think, is about 40 degrees, but I forgot. And you can also notice some other things. Stars that are located away from the celestial pole by an angle that's less than your latitude never set. I know this is a little hard to picture, but you might just want to give this a little bit of thought. Here we are. Here's the North Celestial Pole. Suppose this person looked at the North Star right there. Well, as the Earth spins around, this North Star just seems to go in a little arc like that. It will never set. the north celestial pole never sets, and the stars that are near the north celestial pole, even if they're here, or here, or here, or here, they also go through little arcs in the night sky, and they never set. And I think what I just did is wrong, so let me correct myself. I actually just made a huge mistake. Let me fix it. And maybe some of you caught my mistake. The stars that are near the north celestial pole appear to move around the north celestial pole, not around the zenith. So a star located where my green laser is, right there, it appears to go around in a little arc around the north celestial pole, simply because the Earth is spinning on its axis. So you might want to give that a little bit of thought. Now here's some more examples of exactly the same thing. Let's talk about how the stars appear to move. There's your friend, the Big Dipper again. There's a person. Now you're going to have to picture this. This is a person looking toward the north. By the way, take a deep breath. If you are standing somewhere outside and you're facing north, which I think I am right now, but I'm not sure. If you're facing north, which way is west? You have to kind of think about it a little bit. Think about looking at a map or a globe. But look, if you're facing north, west is to your left, that way, and east is to your right. Obviously, if that's north, that way is south. And as you walk around in life or drive a car or whatever, playing tennis, you'd like to kind of know which way is north, south, east, west, because everything is rising. The sun rises in the east, sets in the west, kind of sets the stage. So here's a person looking north. West indeed is to their left, east indeed is to their right. And here is the North Star, Polaris. Let's assume for the moment that it's right at the North Celestial Pole. And you can see in this diagram, here's where the Little Dipper was at one time. Here's where the Big Dipper was at one time. And then you see in this sort of shadow constellations here, here, and here. And then Big Dipper is here, here, and here. They moved during 6 hours. And the reason the constellations appeared to move, they didn't move. It's just that you on the Earth rotated toward the east, leaving the constellations behind. But because these stars are so close to the North Star, to Polaris, they just appear to go around. You see this arrow? That shows the direction of the sky pinwheeling from the east to the west, because in fact it's us that's going from west to east as we rotate around. You can play the same game as if you're standing looking due south. Here's a person looking toward the south. There's south. And this person, to make life harder, is in the southern hemisphere. So here's somebody in the southern hemisphere looking at the south celestial pole. And if you think about it, and I will leave it up to you to think about it, it is still true that the stars and the planets and the moon rise in the east and set in the west, because she, as an observer, is getting carried in the other direction. Well, the same direction as we always are, toward the east. So she's actually moving toward the east, making the sky appear to go the other way. Fair enough? Okay. Here's a time-lapse photograph of the night sky. If you just leave your camera shutter open for a while, you'll see the stars trace out arcs. Again, that's because we're moving. And here's a quiz question for you. What was the exposure time of this photograph? How long did they leave the shutter open, approximately? I'll give you 15 or 20 seconds to think about it. How long was this exposure? All right, show me your answers. Well, I'll tell you what I see. I see some letter D's and some letter C's, and that's about it. C is 2 hours, and D is 6 hours. It's a tough call. Here's how I did the estimate. I don't actually know the answer. It looked to me like these arcs that you see here are something like maybe 10% of the whole circumference of a circle. Is that 10% of a whole circle? I don't know. Maybe it's less than 10%. But if this were 10% of the whole circle takes 24 hours, so 10% of 24 hours would be 2.4 hours. So I think that the exposure is no more than maybe 2 or 3 hours long. So I would have chosen C. I don't think D is plausible because D is 6 hours, and that's a quarter of a day. So during 6 hours, you should see a full quarter of a circle. And we don't see a quarter of a circle. We only see a fraction of the circumference. So I think it's either C. Yeah, it's got to be C. Is the only close answer, I think. Okay. Now I want to talk about two important issues for the whole semester. The first is, why do we have seasons exactly? How do seasons work? The other thing we're going to talk about is why the moon goes through phases. Let's talk about seasons first. Why do we have 4 seasons? Well, there's some possible answers. The Earth is tilted on its axis, like we mentioned. The Earth's distance from the sun varies during the year. The sun's brightness varies during a year. And maybe the greenhouse effect that traps the sunlight varies during the year. These are some of the answers. You might think of other answers. Why in the world do we have 4 regular seasons? Well, one thing that you can observe to help resolve this question is that when it is winter in the northern hemisphere, it's summer in the southern hemisphere, and vice versa. When it's hot in Australia, it's winter here in North America, and vice versa. So that tells you that answer B is not very plausible, because if you're in Australia or North America, the Earth, if it's carried closer to the sun, even if it were carried closer to the sun in its orbit, it would be closer whether you're in Australia or North America. So I think B doesn't seem very likely. The sun's brightness varies during the year. Well, the luminosity of the sun doesn't vary. The sun is independent of the Earth. The sun couldn't care less about the Earth. It's the amount of photons it emits doesn't have anything to do with the Earth. And then the greenhouse effect is plausible, and it might vary somewhat during the year, but it doesn't change the amount of direct sunlight. Greenhouse effect has to do with trapping heat, which we'll talk about in a few weeks. So the best answer, it turns out, is A, and that actually is the right answer. Seasons are caused by the tilt of the Earth's axis. I'm going to show you some diagrams of this, and in advance I'll let you know that at Harvard University, they have polled the graduates, the people getting their bachelor's degree from Harvard University, were given a quiz and asked why we go through seasons, and more than half of the Harvard graduates said it's because the Earth gets closer to the sun or farther from the sun. So that tells you something about Harvard. And they all got A's in their astronomy class. Everybody gets A's. So here's a diagram. There's the sun again. the Earth goes around once a year. We already talked about one astronomical unit is the distance, 150 million kilometers. The Earth's orbit actually is not a circle, it's an ellipse. We'll talk about that later in a week or two. But here's a better diagram. There's the sun, and then of course, there's the Earth with its spin axis tilted 23.5 degrees from perpendicular to what? Well, perpendicular to its orbital plane, the gray ecliptic plane. The tilt axis here is 23.5 degrees to the perpendicular to that plane. And so here's what happens. During the year, during 12 months, there's the sun, and at times the Earth has its north hemisphere, the North Pole, tilted 23.5 degrees toward the sun. And so if you happen to be in the north, you're spinning around the Earth, the northern hemisphere is pointed more toward the sun. The sunlight is coming more directly down. In other words, it's more nearly overhead. And moreover, the days last longer. The days last longer because you can see if you're up here on the Earth and you spin around, you spend a long time in daytime and then just a little tiny amount of time in darkness. The nighttime is only 6 or 7 hours long, but the daytime could be 16, 17, 18 hours long because of the little arcs we make in our lives as we spin around the Earth. That's what it looks like in summer in the northern hemisphere. In winter, the northern hemisphere, you see, is tipped away from the sun. So now if you live near the North Pole, you're in permanent darkness. If you live within 23 degrees of the North Pole, you just spin around, you're always in darkness, you never see the sun. If you're at latitude 37 degrees, like here in San Francisco, you spend a little time in daylight, but a long time over here in darkness as you go around. So the days are shorter in the winter, and the sun hits at a glancing angle. You see, if you're in the north, suppose you live right here, that's your body standing upright. The sun makes a glancing blow. So the light is getting spread out over a larger surface area because the sun is low on the horizon and the light is getting spread out over the area. The same amount of light is getting spread over a larger area. So you get less solar energy that heats the ground per minute during the winter. And then, of course, during the fall equinox, so-called, the first day of fall, when the amount of daylight and nighttime is equal, fall equinox, you see the tilt angle is sort of off to the side. We are neither tilted toward the sun nor away from the sun, we're sideways, because the spin axis of the Earth always stays fixed, at least over the course of centuries. And then, of course, obviously, there's the spring equinox, when there again, the tilt axis is neither toward or away from the sun, it's just sideways. So the length of the day and night is equal on the first day of spring, March 21st, and the first day of fall, September 21st. Okay? And by the way, the first day of summer is called the summer solstice. That always happens around June 21st or June 22nd. And of course, the first day of winter always happens around December 21st. And ancient peoples had huge celebrations on December 21st because they knew that after December 21st, the days would get longer, the sun would be higher, the air would be warmer, and they'd be able to grow crops again and do their agriculture. So the time around December 21st was always a huge time to celebrate. And here's another picture showing the same thing. Here in the northern hemisphere, when there's summer, the sunlight is hitting more directly. The light is spread over a certain area. But there in the winter, you see the shadow of that person. The sunlight gets spread over a larger area when the tilt axis is away from the sun. That's what causes winter. And here's a little video that shows all of this. You'll see a whole year go by. So watch, there's the Earth in summer, tilt axis toward the sun. There's the autumnal equinox, the fall equinox. Now the spin axis is pointed away from the sun. That's winter for the northern hemisphere, but it's summer for the southern hemisphere. And then here is the spring equinox. And now we're heading into summer again, with the tilt axis pointed toward the sun. Here in this box down below, you're seeing the perspective of somebody living on the Earth and where the sunlight comes from, the angle that the sunlight hits us as you go through the course of a year. So the seasons are predictable simply because the spin axis is pointed toward the sun a certain time of the year near June 21st, and away from the sun on December 21st. And now I'm stuck. I knew this would happen. There we go. Okay, now we're heading toward ending our discussion of the seasons, and we're going to discuss what is really the most exciting part of the lecture, which is the phases of the moon. I'll just summarize the seasons. Uh-oh, I thought I would summarize the seasons. I can't get rid of that movie. The movie has a life of its own. Oh, I literally cannot get rid of the movie. This is so funny. The great thing about this here, I'm going to try. So I honestly, I cannot get rid of the movie. It's hilarious. The movie will be with you for the rest of your life, as far as I can tell. Let's try one more time. Did it stop? It's really funny. Let's see, swap displays. Let's try a few things. That looks promising. If only it really were summer all the time, but instead it just keeps going back and forth. No, this is really, really funny. I cannot get rid of that movie. I think if I throw this computer, like out the auditorium, that movie will still be playing. I'm going to try something drastic. Actually, I can't try anything drastic. It's really, really funny. I'm not going to power down my computer. That I can't see myself doing that. Do you have an idea? Anyone have an idea? Sorry?
Press Command Alt Escape, and then you can force quit Safari.
I've already quit Safari. Oh, Safari. Safari. Wow, that's a brilliant idea. Let's see if that works. I've never had this happen before either. It's really kind of hilarious. All right, here we go. Here we go. Ooh, so exciting. We killed the seasons. All right, so now we're going to talk about the moon and the phases of the moon in the last 15 minutes of the lecture, I hope. All of you have seen the phases of the moon. Let me remind you those phases and tell you their formal names, because you'll want to know them. We'd like to know what conditions lead to the phases, but also what causes eclipses. We're going to have some fun eclipses during the semester, a lunar and solar eclipse. But here are the phases of the moon to remind you. Some of these may be new names. You start off with a new moon. By definition, a new moon is a moon you can't see at all. Then there's a crescent moon, very beautiful, as of course you've all seen. There's a moon that's half lit. We call it a quarter moon. I don't like this name too much. There you see essentially half of the moon lit up, but we call it a quarter moon because this is one quarter. There's a backside, 3 other sides, so that's called first quarter. Why first quarter? Because it's the first time you see a quarter moon. We're going to see a third quarter later on. Here's called a gibbous moon. You might not have heard that word before. A gibbous moon is a moon in which more than half of it is lit up. And then, of course, there's a full moon that all of you know about. There's a gibbous moon on the way back and a last quarter moon. Here they are, gibbous, last quarter, crescent, and then new moon again. Every 29.5 days, the moon goes through its full sequence of phases, new, crescent, first quarter, gibbous, full, and then back through the cycle again. When the moon is getting bigger, we call it waxing. And when the moon is getting smaller, we call it waning. So we talk about a waning crescent or a waxing gibbous. That tells you not only the shape of the moon, but whether it's getting bigger or smaller. Waxing is bigger, waning is smaller. Okay? Why do we get the phases of the moon? Hang on to your hats. This is one of the most important points of the whole semester. Here's a picture of somebody observing the universe. She's holding an imaginary moon in her hand, and the sun is over here. So there's the sun. The sun is what illuminates the moon. One side of the moon, one hemisphere of the moon gets lit, and there you see it. There's the sun. It's illuminating that half of the moon. The other hemisphere of the moon is dark. So when she looks up at the moon, the way she's holding it here, she looks up and she sees the dark side of the moon. She cannot see the lit side of the moon because the sun is illuminating only the other hemisphere. She looks at that moon, it's fully dark. That's a new moon. And you can see it's labeled as such right here. There's new moon. Okay? Now, if you imagine, and she's doing this, moving the moon over here, now when she looks at the moon, the sun is still illuminating that one hemisphere, but she looks at the moon and she can see that piece right there. It's just a little sliver of lit hemisphere. The rest of the lit hemisphere she cannot see, and that's why she sees a crescent. Indeed, it's a waxing crescent. It's getting bigger and bigger as that moon moves around her. So here's a waxing crescent due to the fact that she sees only a tiny fraction of the full sphere of the moon being illuminated. Most of the hemisphere that's illuminated, she can't see. And then a quarter of the way around, the moon is over here. When she looks at this moon, she sees half of it lit and half of it dark. And so she sees this, a quarter moon. You call it a first quarter or a waxing quarter because it's getting bigger. Over here, she sees most of the moon illuminated. So here it is, mostly illuminated. That's a gibbous moon. And then when the moon's over here, the sunlight is hitting all of the hemisphere she sees, assuming her head is not blocking the sunlight. And so she sees a full moon. And then as the moon continues on, the portion of the illuminated hemisphere changes continuously. During the course of 1 month, 29.5 days, as the moon orbits the Earth, in 29.5 days, she will see it go from new moon to crescent, a little sliver illuminated, quarter moon, gibbous, and so on. And so you always get to see some combination of the lit and unlit portions of the moon. Sometimes you see almost none of it lit, and that's the new moon. And sometimes you see almost all of it lit, and that's a new moon. This is a demonstration again. I'm frightened to death. Yeah, this is really interesting. Yeah, I don't think I can do this. Fascinating. This requires me to have control, and I can't get control. This never happened to me before. It's really kind of interesting. And the great thing about it is, I have to get out of Safari again. I'm going to do that because I only have one or two more slides, and then I want to show a demo. So let me try this. Yeah, I actually have only one more slide, and I don't even want to do my slide. I'd rather do the demonstration. So hang on to your hats. I want to do two demos. Luckily today I brought the moon with me. There it is. Now, it's interesting. For me, these lights are illuminating half of the moon. You out there can't see that the back half of the moon is dark. Some of you can see it if you're off to the side. You see a nice quarter moon. But I want to try to do this a little bit better. So, thank you. So I've brought the sun right here. And if we could have the lights in the auditorium dimmed all the way down to get rid of those suns. We don't need any other suns around here. I got my own sun, thank you very much. So I brought this sun, and what I'm going to do here, I'm going to dim this light too for the moment. And I think you'll be able to see here, if I can point toward the moon. Can you all see a full moon there? Oh, this is going to tax the camera work of the people in the back of the room. See, they can't find me. That's the funny thing. If I run around, then the camera person can't find me. That's really funny. What they're looking at is the board over there. Yeah. So you should just watch me, I think. You should be able to see, oh, there we go. There it is. Yeah. So this is a full moon. And now I'm going to move the angle of the sun over here. Do you see a quarter moon? And then I'm going to move the angle around a little bit more. Do you see a crescent? Of course, all of you are in different you're different Earths, and so you see a different vantage point. Do you see the, by any chance, a crescent? I can't tell, of course. Only you can tell me. Quarter? How about now? Yeah. How about now? You see it? Yeah, these folks over there see a new moon, and then, uh-oh. Now what about that? Some of you on the side see a crescent. New moon over there. Do some of you see a crescent? And there's a quarter moon again. And here's a gibbous, for most of you anyway. And then there's a full moon. How's that for a demonstration of... So we can have the room lights back up again. That's the end of today's lecture. Good luck with your homework due tomorrow.